Hey everyone, this is Dr. Walker. In this video, we're going to do another example going over the superposition principle. So trying to find a net force on a charge, and we will use unit vector notation. This is example 506b.2. The example says, what is the force on the charge Q at the lower right-hand corner of the square? We have four identical charges at the corners of a square, and I've numbered them 1, 2, 3, and 4. What I've also done is I've labeled the distances between each charge and charge 4. We're trying to find a net force on charge 4. We know that like charges repel, so this charge 4 here is going to experience three different forces. It's going to experience a force away from Q1 called F14, is also going to experience a force away from Q2 called F24, and is also going to experience a force away from Q3, F34. So to find a net force on Q4, we have to add up these three forces. We can write that over here. This is our goal, is to find F4, and we're going to do that by adding F14 plus F24 plus F34, and we are going to use unit vector notation. So the other thing I have also labeled here is each unit vector. Remember that when we write down Coulomb's law, which I have already written here for each force, I have written Coulomb's law, Coulomb's constant, times the product of the two charges divided by the distance squared between them, times the unit vector. The unit vector is from the first charge towards the second charge, towards the charge that we're trying to find a net force on. So our job now is to just fill in what we know for each of the three forces, and then we will add them. So let's take a look at F14. For F14, we need a distance R14. We can see that that's the hypotenuse of the triangle formed that has legs A and A. So if we use Pythagorean theorem, square root of a squared plus a squared, that's going to give us square root of 2 times a. So we can write down Coulomb's constant, and then the charges, I numbered them just so I could more easily refer to them, but each charge was actually called Q in the problem. So we can just put Q times Q, which is also Q squared, so we can just put Q squared for the product of the two charges. Then the distance R14 is square root of 2 times a, so we need to go ahead and square that. So that's going to be 2a squared. And finally, we need R14 hat. So how do we find that? Well, let's find it on the side over here. R14 hat, by definition, is the vector itself, R14, divided by the magnitude of R14. How do we write down R14? Well, R14 is a vector that has a length R14 and it has a direction R hat sub 14 here. So we can imagine a vector just going from Q1 down to Q4. So how do we get from that position to that position? Well, we have to go to the right by distance a, and then we have to go down by distance a. So we can write this vector as a in the I hat direction minus a in the j hat direction. So that is how we can write the vector R14. That way we have not only its direction, but also its magnitude. And then we already said that the length of R14 is square root of 2 times a, so the a cancels out. So for R14 hat here, we can write down 1 over square root of 2 times I hat minus j hat. This was actually the hardest one. The other ones are easier. For F24, we can write k q squared, and then the distance r24, the distance between charge 2 and charge 4, and we can see that it's just the length of the square, which is a. So we're going to square that distance. And then what is r hat for the 24 here? Well, r24 is going down, so that is simply negative j. And we know that j hat is a unit vector, so that's all that we have to do to find r24 hat. And finally, for f34, it's very similar, Coulomb's constant, q squared. The distance 34 over here is a, so we're going to square that. And what is the direction of r34 hat here? It's in the I direction because it points to the right. So we have written all of our forces, and now we need to add them. To add the forces, we just have to add the different directions separately. So let's go ahead and do that. F4 is going to be equal to all of the components in the I hat direction. So this component of F14 and this component of F34. Now they do have a factor in common, the keq squared over a squared. All of the components have this in common, so we can factor it out. Keq squared over a squared times 1 over 2 square root of 2. That is the I component of F14. And then for the F34 component, it's just going to be plus 1. This is going to be in the I hat direction. And then we're going to do the same thing for the j direction. And actually, instead of writing a plus, since both j's are in the minus j direction, we can just write a minus here. We can factor out our keq squared over a squared. The j direction for 1,4, we still have the 1 over 2 square root of 2 component, a factor. And then for the F24 component, we just have a 1. So all of this is the j hat direction. So this is our final answer for the net force on charge 4. It does look a little bit clunky, but if we had values for the charges and for the distances, we could plug them all in to get a very simple answer in terms of I and j, so in terms of the unit vectors. So hopefully you enjoyed this example using the superposition principle for Coulomb's law and unit vector notation.